Sure. Excuse me.
The worst
I know
of
what
all.
you're fucking.
Favorite class.
Oh my god.
Not talk to yourself.
Yeah.
Good job with the fucking.
Oh.
What? You just do return
No, if it's like if you do like if it's a no, if your object is null, it's like null dot get. Second sure.
Just check. Yeah, first it's
Yeah.
Just check if key equals null.
That's why I checked. It's a dead code.
Test 1, 2, 3. Waiting for the projection off.
I'm waiting so hard. Oh, okay. I think I know. Say I'm gonna go at. I was catching a moment with you.
Today we will review kernel read regression and the kernel tree in general. We derive kernel ridge regression from the dual solution to ridge regression, where we can express the optimal weight. I know nothing's up. I'm buying time. Buy time for microcode reboot or somehow set it up. But I don't want to waste time per se. So starting from the dual solution to kernel regression, using the fundamental theorem of linear algebra, which says if I have a matrix X, every point in this ambient space can be decomposed into sum of two vectors. One lies in that space, it's within the span of that matrix, the column matrix vector, the span of the column vectors. The other is in the null space of that column space. So if we represent each vector in terms of the direct sum of such a decomposition, we will show that ridge regression forces null space component to be 0. Because of that, the optimal weight vector can be represented as a linear combination of the columns vectors, which is just the instances you have in the training set. With that view, we can re-represent the weight matrix as some weights over the number of instances, and then we can derive the solution. That in itself is not that interesting or useful. It's the fact that once I have that representation, I solve the optimal combination coefficients over the training instances. Then when I need to apply my optimal model, I only need the dot product, the instance similarity between a new instance and every training instance in my data set. So I don't need to find an explicit representation of the weight matrix. All I need to know is the similarity between the test instance and each training instance. You see, the linear combination coefficients have absorbed the variable y, the target value. Right? That you don't see y anymore. Y is absorbed into this combination coefficient, so-called beta. Beta is actually a linear function of y. Okay? Now, so now if solving the combination coefficients requires so-called a Gram matrix, which is training instance similarity, pairwise between that. The evaluation of the model only requires the pairwise similarity between the test instance and each training instance. So all we need is just inner products. So I can have a function that takes two vectors in, two input vectors in, spit out the similarity, which is just a scalar. Okay? That's the idea of a kernel. You can certainly compute the kernel by taking this feature and do the dot product. The beauty of the kernel trick is to say, sometimes you can get a value without explicitly calculating the feature themselves. So this is better understood if we go for the kernel ridge regression. So instead of applying ridge regression to the original feature space, we lift the original input to a most likely higher dimensional feature space. It doesn't have to be, but most times we go for a higher dimensional feature space. And then we apply just ordinary ridge regression to this lifted feature space. So then, in that application scenario, from the dual solution, what we have is just inner product between the lifted features. And the kernel over lifted features can be computed as a function over the original input vectors. This is where the power comes in. Okay. So I want to check with Michael, see How much more time does he need to fix this? It's coming out. Okay. So he's panicking. So how can we help along? Okay. At this point, do you have any questions? Yes. Yeah, very good question. In the primal solution, we also use inner products, but inner products is between it's between the, you know, we have this distinction between covariance matrix and Gram matrix. Both of them require inner products. Okay. For the covariance matrix, you have X transpose X. Okay, so from each instance point of view, so you have each instance d by 1 vector times the horizontal version of it. So that gives you a d by d matrix. The second instance come in, you take that d by 1 times this horizontal version of that, another d by d matrix. Covariance matrix summation of all these d by d matrices. Okay? In the end, it's a d by d matrix. So what does the d by d matrix tell you? It tells you how similar the values in different features are. For example, if you have, one example I have given a couple of times is this. You have go out to this 1 million people, you measure height and weights. Your office mate comes in and do it again. He's not aware that you have done the measurements. He takes he put it in another column, and then we assume it's a different feature vector. So these 1 million measurements, the first height measurement you take and the third height measurement your office may take, they're highly correlated. Okay, so no matter which instance you look at, you have this, d by d, the one that corresponds to this 1 and 3 entry correspond to exactly the same measurement will have very high value. In the Gram matrix though, it's X transpose. Each row of X is all the measurements related to a single instance. When you do this dot product, it gives you the instance similarity. First instance with respect to the first one, first instance with respect to the second one. At the end of it, you have n by n pairwise instance similarity matrix. So, and then if you look at the form of it, both of them require some either covariance or Gram matrix plus some lambda I. And then you take the inverse. Matrix inverse is most expensive. It's at a computational complexity of, in the big O notation, it's n to the third power. Okay? So if I go for the primal solution, I'm dealing with the d by d matrix. If I have 1 million instances, my measurement is only 100 attributes, then I marginalize over the number of instances. I end up with the 100 by 100 matrix. Solving the inverse of a 100 by 100 matrix is much simpler. In the dual solution though, you will have to deal with 1 million times 1 million matrix. That inverse scary. So we will get to that. When should we use the dual solution? When should we use the kernel trick? Okay? So even though inner products are used in both form of the solution, what is dot product in what makes a difference? Does that help? So that's very interesting. The question was, so can we use a trick on the primal form of the solution? I think this actually has, you know, in terms of formality, they both have this X transpose or X transpose X. But the way we derive dual is not just a simple matrix manipulation. It's based on this decomposition into the, you know, column space and a null space. And the fact that at the end of it, the dual solution is a linear combination of the original instances. But in a way, I think the question is very inviting in the sense that there are a lot of primal dual approaches. So there is, you know, you want to seek the solution in the primal space because it's most natural. You formulate the formulation criteria. But you turn it into dual. It's like, you know, it's the same, two sides of the same coin. You flip over and say, okay, if I use that representation, which is equivalent, I get a different look. But then you can apply dual to the dual. That's what you're saying, right? There are problems like this. Sometimes you actually have benefits of both. Because of this trade-off, if n is greater than d, most likely you would like to go for primal approach. This is just for the sake of computational efficiency. But as we know from the kernel trick, kernels buy us two benefits. One is computational efficiency. Two is this modeling power. Sometimes even you know, I may, with the cost of computational efficiency, I can achieve more modeling complexity. I will still want to use kernels. So there is a trade-off. For those of you who know Fourier transform, FFT, how many of you know FFT? Okay, so you know FFT is you know signal, a raw signal in the spatial domain versus Fourier transform in the frequency domain. When you calculate this, there's also a trade-off, right? So when you should use FFT, when you should just use a little filter. So sometimes you know, when it's a certain size, you want to go for FFT. When it's beyond certain size, you're better off with the original filtering in the signal domain. So depends on how you're using the approach. I find that, you know, kind of going between primal and dual is a very interesting direction to investigate. So keep the thought in your mind as you learn more. Very good questions. So let me see, what can we do with pure talking? We have a lot to widen. I'm hoping it's not such a catastrophic technical problem. I mean, how hard could it be? Just seriously. Usually it's just a little thing. Yeah. But let me think. Okay. One way to look at the dual view of the solution is look at this. Oh, you have a question? Okay. So why don't you go to www.icsi.berkeley.edu, icsi.berkeley.edu. Okay, why don't you try first? If it doesn't work, I write it down, okay? www.icsi.berkeley.edu, ICSI, I-C-S-I, okay? / Stella YU, my name, /1/1.pdf. Now you know. Anybody getting it? It should work.
So can you
www.icsi.berkeley.edu / Stella YU to get all together /1/1.pdf.
you said that as no at the beginning?
We don't have permission.
Raise your hand if you look in the file.
What?
Oh, it will redirect. It will automatically direct. Don't worry about it.
Oh, she said slow this.
Magic.
But he also knows
Do you get it? Okay, let's get started. So we have kernel ridge regression. We have, let's go to the slide on kernel trick, okay? So all we need is some measure of pairwise similarity, and that's just a scalar number between two instances, x and z, which correspond to the inner product in a lifted feature space, h of x and h of z. The key thing is we may not need the lifted features, hx and hy themselves. So the kernel trick is to never form the actual lifted feature vector. Instead, we use a function to calculate this. Equation 7, it is the, if I go to that lifted feature space, it has to be defined as such. But the result of that doesn't require h in some cases. So there are two benefits of kernels. One is for computational efficiency. Two is flexibility to expand function families. Next slide is example. Let's say I have a 1D to a 3D polynomial lifting, okay? I just have, original feature is just a scalar x. My 3D polynomial lifting takes a 0th order, 1st order, and a 2nd order, okay? With some coefficients in front of the polynomial terms. Now, in that, if I use explicit kernel function, I'm going to take the 3D feature vector h of x, and calculate the inner product. Yes? That's equation 9. Okay? This by itself, if you look at the, it's a2, x2, xz2 plus a1, xz plus a0 squared. Right? This itself is a function only contains xz. So you can consider this as just a proper kernel function. Okay? It's a kernel function corresponding to a 3D polynomial lifting. But there's another way. If I look at this, look at equation 10, okay? I just calculate inner product between x and z, and then I let it pass a nonlinear function, plus 1 and a square, okay? And if you compare equation 9 and 10, you can see that they are equivalent when the A0, A2 is 1, and A1 is square root of 2. Which means when I take a particular form of combination coefficients, I can evaluate in a different form. In the lifted feature space, inner products can be computed from a linear function of the inner products in the original space, which is much lower. Yeah, question? Oh, sorry, A1 should have a square as well. Yeah, thank you for catching it. Okay. Okay, let's see. Okay, we'll just continue. And if this is just a case of polynomial order p equals, it's just the second order. If I raise to the power of 10, I'll have many of these terms, right? So the saving in computation is much more significant, right? Because x and z is just 1d, it's just one number. I add 1 to it, and then I raise to power of p. That's a very minimum calculation. If I have to lift it into 20, 30 dimensions and do the dot product, I have much more computation to do. Now, next slide is to illustrate. It's not just for the saving of computation. There is a power when we lift the feature from low dimension to high dimensions. In this plot we showed last time, we have two rings of points. One is red dots, the other is blue circles, blue triangles. Ideally, we want, in a few weeks, you're going to learn classification. We want to classify them into two classes, red class and blue class. It will be impossible to separate them in the original space by linear functions. Any linear function, just a line. It's not linearly separable. But if I use this, polynomial kernel lifting to 3D, essentially those located at a larger magnitude are lifted to a higher altitude, and the one that closer to the origins remains in the inner circle. And then I can just find a vertical plane, there's a linear function to separate them, okay? This is to illustrate feature lifting brings additional modeling power. You can apply linear function in the high dimensional space, yet accomplishing nonlinear functional families. Next slide. We have, so it's nice to think of, instead of individual feature, when you do feature lifting, you have some h of x. H of x could be any nonlinear function you think of. It only depends on the instance, the feature vector value themselves. When we are dealing with a kernel function, every time we have to take in two instances. But the question is, can I just construct any pairwise function and then treat this as a kernel function? The answer is no. Not every pairwise function can be a kernel function. A kernel has to meet the condition of being a kernel, which is that there must exist some lifted feature h of x such that k over xi xj is the inner product of h of x and h of xj, the inner product between the lifted feature. Okay? So liftings and kernels are equivalent. If you have a lifting, you have a corresponding kernel function. If you have a kernel function, there's got to be a lifting, associated lifting. Now the question is lifting unique? Just think about linear algebra, inner product, Vector A transpose B, just these two values. When will A transpose B equals A transpose, some other A transpose other B. Is it possible to have different liftings yet lead to the same kernel function? Inner product. If I have these two vectors, inner product, if I rotate both vectors, does the inner product change? Does it change? Just rotation. It doesn't change, right? Intuitively, in 2D, for example, what's the inner product? Two vector, essentially, the inner product of two is the magnitude of this times the magnitude of this and the cosine of their angle. So if I rotate, none of these three quantities change. The magnitude doesn't change. For either of them, the angle between them doesn't change, right? So liftings are not unique. So now, there are two ways to quantify the kernel function. We want to have the freedom to construct a kernel, because that's the point of this view. Just look at the pairwise function without going for this explicit feature lifting. So if K is a kernel, then the n by n pairwise matrix, it forms on any collections of x1 to xn, any data set in the domain. It must be a positive semi-definite matrix. What's the definition of positive semi-definite? If K is positive semi-definite, PSD, then take any ambient vector Z. Z transpose K, Z has to be non-negative, right? The quadratic form with K as a matrix has to be non-negative, yes? So this is easy to prove. As if you follow equation 17, 17 is the definition of a kernel. If it's kernel, there got to be some HX. I assume it exists. It has to be. That's the definition of kernel function. 18 is if I write out so the pairwise matrix formed over a collection of instances becomes, simply H transpose. H is the lifted feature for every instance. And then if I want to test whether it's PSD or not, I apply the quadratic form, Z transpose KZ, and that will be Z transpose H transpose Z. And that essentially the H transpose Z is a norm. It has to be non-negative, right? That's easy to see. Now, so this is a one test, just numerically. If I can show that this is the kernel matrix form is instantialized on any set of instances, is always PSD, I know that K is a kernel function. Turn this around. If I have any PSD matrix G, then I can always, show that it is a matrix of inner products. That means it has to be inner product of some lifted features. Okay, so that's just through SVD. There is equation 20 and 21. You have to be a little careful because if I apply SVD to G, I will have U S transpose, and the G IJ is, you can define an equivalent feature vector, but this corresponds to the ith row of US transpose, and that is not the usual thing. It's actually the first row of the U matrix, but each entry is scaled by different singular values. But that's just a proof and some intuition to have. So now, how do people come up with a flexible way of constructing kernels? This is the usual approach to it. Instead of just inventing one, two kernel functions. Sure, yeah. Where? Where is? Yeah. It has the. Where did it go? It has a little. Oh yeah, right here. So there are some commonly used kernels. The first one, of course, is this linear kernels. That's the usual inner products we use. And then there's a polynomial kernels. We have already used a couple examples. And then there's a sigmoid kernels. Essentially, it's a nonlinear function. It's a tanh function over the inner product in the original input space. Beautiful. Thank you, Michael. Can I go back or should I stay here? Stay here, okay. So, thank you everyone for being so patient and so gracious. And then we have the Gaussian basis kernels. Essentially, and that is actually x minus z, right? This is essentially that. It's still in a product in the original space, but it's the difference vectors in the product. Now we have something we know it's like a seed functions. And to make it more complicated versions, we can prove a bunch of composition rules. So if we can use existing kernel functions to construct more complicated kernels. For example, linear combinations of kernels. If the linear combination coefficients are non-negative. The product of kernels, two kernels, if each is a kernel, the product is also a kernel. And then there's a weighted kernels. It corresponds to some feature, but each feature I will use different weighting. And this sigma has to be PSD, okay? And this is a feature vector, but I can also use a kernel, and so this sigma is fixed, constant, no matter which x and z comes in, right? But here I can also use a feature weighted kernels. So the kernel is fixed just like this, but I have a scalar. As a function is a scalar. How good? By looking at the feature, what is my s? And you multiply it. Each of this you should be able to prove, and it's very simple to prove. You have to grasp what is a kernel. It has to correspond to some feature in a product. So long as you can prove that, it is a proper kernel function. And we have shown that Gaussian kernel can be expressed as a inner product between infinitely long feature vector. Again, this is not the only way, but this is one usual way to do it through the polynomial expansion. Okay? And so if you look at this, the RBF kernel itself, Gaussian RBF equivalent, because essentially it's capturing, it's just a bump. It doesn't matter where they are. If you hide 3D, doesn't matter where you are. It's only the distance that matters, radius that matters. So this is in the raw feature space, whatever D dimension, and in the lifted space, M is actually to infinity long. So this is a very powerful lifting. So this is a diagram you should keep, may help you understand the concept. Original feature, I can go through this route, calculate the kernel function. First, I lift to the feature space, and then I do the inner product. The kernel trick is to say, do not go for explicit kernel calculation. Calculate something just based on X and Z, okay? And here we have this actually means PSD, okay? It doesn't mean every entry is non-negative. It's more than that, okay? Now we can take this ideas a step further. There's a thing called a representative theorem. Consider a general optimization problem. We have two terms. One is data fitting error. Okay, this error. We don't need to be concerned with the form of this error function. What we have done is the least square error. Okay, but it compares two things. One is the target value is y. The other is a linear function, w and xi. It's in the product between some model and xi. In a way, you can think of it as a template matching. You have w is the model, the template you're looking for, and every instance you need to be compared with that. Okay, and then there's use R to go for this error term. This is a regularization term. It's a prior you applied in the model space, and this is a function over the L2 norm. Okay, so of course you can square root of it and go for the norm, but the fact that it is an explicit function of the L2 norm. So we can follow how we derive the kernel ridge regression and the kernel trick. We apply the fundamental theorem of linear algebra. We can write W as, because here you have inner product, you have this linear combination of that in the range space and in the null space. Okay, the definition of null space is that any null space vector times anything in the column space, that has to be 0. They're perpendicular to each other. So we plug in this equation 26 into 25. The inner product and the linear combination can be expanded. It becomes the inner product between W and each of the xi. So here I have this comes from this sigma comes from this. I have to use J so that they don't repeat. And so this involves the inner product between xi and xj. Okay? So essentially it's sigma j equals 1 to beta j xj, that's my W, plus this thing, plus xi in equation 25. And this equals, I can take sigma out. You have beta j and xj xi. And then you have a term which is W and X in the product of that. Okay? And we know, according to the definition of the null space, this doesn't contribute to the prediction. So this will be 0. Okay? So I have a function over the first term, and the second term, because it's a direct sum, it's a range of x plus direct sum of null space of x. So if any vector belongs to this, if any vector is decomposed into two orthogonal components, the norm is essentially the norm, the norming in the individual subspace and add together. That's how you get this equation. Because the cross term is 0, they are orthogonal to each other. And now this function, initially you're optimizing over both beta and the W, the null space component. And the only thing involves the null space component is this term. Since you want to minimize this, you might as well set it to be 0. So that's why this is gone. So this is what you end up with. So we introduce Kij as the inner product between xi and xj. And this is a quadratic term, and you can verify it's just the quadratic term using k as the weight, as the inner product between xi and xj. Now, if you look at this, we are not talking about any specific error function or regularization term. Just look at the variable. It only contains what is unknown. K is known. K is known. Beta is the only thing that I don't know. Yi is known. So it's a function of beta only. And I can solve this with a, say, gradient descent or something. Likewise, follow how we get to the dual for ridge regression, kernel ridge regression. So this problem only has m parameters on beta 1 to beta n. It doesn't matter how large the feature dimension is. If I have 100 points, each point has 1,000,000 dimensions, then it's a huge saving. And the solution can be evaluated only with dot product, because this W star X is simply, because it initially is represented as some xi times beta I plus this, but this is 0 as we have shown. So essentially, when I evaluate on particular x, it becomes xx inner product weighted by beta I. So here we come to a very general kernel trick. You just replace this with this function. And then this term, you can see this is essentially matrix K multiplied by beta, and the I is taking the row, so it's ith row of this value, okay? And we can solve this, optimize this by solving this beta star. Once we solve that, when we evaluate this K, we use a lowercase to indicate it's a function. It essentially evaluates the similarity between xi and x, okay? This is just to show that what we have learned is not restricted to ridge regression, where you have this, L2 norm on the prior, you have this least square error function. It can be very general. You can have very complicated error function and a different kind of regularization term. So long as it takes this, it's only a function of this, takes this form. It's only determined by the inner products between the model and the instance, and the norm of the model parameters. Then this kernel trick also applies. So when should we use kernels? Every time we introduce a new trick, through some extension, we have a probabilistic view, we extend it to different color noise, different priors. We have, now we are going for the dual solution, and we make a connection, we can extend it to the lifted features. Every time something new comes in, we have to ask ourselves, when should we use this? Good thing about kernel is it never needs more than n parameters. N is the number of instances. And the second thing is it allows us to engineer nonlinearity with minimum added complexity. Think about RBF kernel. Think about polynomial kernel. I can have a choice of P. I just need to change a P. I have a whole different families of functions. And try to do that in the primal space. you expand to the lifted space, for different P, you have different feature vector to evaluate, right? The downside to kernels is that it needs to store the entire data set for testing. Because at the test time, you have to evaluate the similarity between incoming test instance and every training instance. The second thing is the kernel matrix is n by n. That can be very large. And there's certainly a lot of speed up routines to solve large scale matrix inversion, for example, or even when you evaluate the function, there are ways to speed up. Or you can sample, but this is a downside we cannot ignore. So far we have, the most comprehensive view about the regression model we have is this maximum posterior view with a generic prior and a color noise, right? Everything we talk about can be summarized here, right? And all in all, we deal with this model. This is our generative model of data, right? We have X, and we have this is model parameters, which is random variable, and it may take different priors, and then we add some observation noise and we get to the target values. And this slide is taken from previous lecture, and it shows how we can write it out into this joint Gaussian random variables. If you look at the structure of it, Y is my observation, W is a model. It's re-represented by some unknown IID variables. One for this U is for the noise. V is actually for the prior, for the model space. Okay? It's just reparameterization. Look at this matrix. This matrix is completely known. RZ is for the noise. RW is for weight. X is given, is fixed. There's nothing you can do about it. And RW is also for the weight. Okay? So U and V is to be recovered, and this 2x2 matrix only contains known quantity. There's no unknown variables there. And we have Y, we don't have W. So essentially we don't know this, we don't know this, we don't know this. But the relationship between the two sets is just a linear, known relationship. Okay? Today, we are going to handle, there's a noise in X. Okay? So far, X doesn't have any noise. In the ordinary least square, the rest is just, sophistication of different priors, different color noise, but we never touched X. We only handle Y, make sophistication to Y or W. We never touched X. And we treat this as independent variables. These are domain, these are how I decide where to sample my observations. In total least square, we assume there's a noise not only in Y, but also in the independent variables. This is also some measurements I need to take in practice. It's not like I need to calibrate a device. I say, try to get a value at the equal intervals. So I know I'm getting to that. But even to know that this is a measurement corresponding to a particular interval, I need to take a measurement. Whenever you measure it, you have a noise. So X also contains noise. So now if you look at this, in this model, X, some ground truth noiseless version, add some random noise, okay? Then you multiply with W, which is unknown. When you have a model W multiplied by some noise, that makes a linear solution very hard. In a node, there is a 1D example, but you can see that reason why. If it's just some unknown with some fixed matrix, that's easy to handle. And you have least square criterion. It's essentially a quadratic optimization problem. You can have linear solutions. But when you have something that is product of two unknown variables, that's no longer a linear problem. So today, for this problem, so-called total least square problems, here in the original least square problems, x and y, the rows are asymmetrical. X, you don't question it, ground truth, Y is something you assume there's noise in it. But in total least squares, both x and y, you lose, you lose this, what is x, what is y. They both have noise. The only thing is, at the test time, you are given the x, you still want to predict y. This is one direction. That's the only row difference. But other than that, in terms of nature of the measurements, they are equal. So for this problem, total least square problem, you can see that taking the probabilistic view with MAP is not going to lead you to an efficient solution. We're going to introduce a new approach, take a different view. We treat regression as a low-rank approximation problem. When we were using the probabilistic point of view, we assume finding the model is to find the most likely solution within the model parameters that can generate this data, right? This is MLE's view. MAP's view is just add a prior to it. You have some preference. But in the low-rank approximation point of view, it is the following. We want to minimize this. So I might as well call this residual, right? Any W, I have prediction, I minus Y. I cannot predict Y perfectly. There will be a difference, and that's the residual, data fitting residual in Y, okay? So minimizing this, I just change variable, EY equals this, so I'm essentially it's minimizing EY. But I subject, because I introduced this definition, I need to put this. See here, initially I only have variable W, but I introduce a new variable, EY. If I have n instances, W is D by 1, EY is n by 1, right? So now I introduce more variables. But the thing is, I have a known constraints between the two sets of unknowns, W and EY, and that's given by this equation. Nothing fancy, it's just introducing this concept, predicting minimizing the fitting residual, and the residual comes from, this fitting error where you have this underlying model, W. Taken from this view, total least square essentially is we extend it to TLS. We try to minimize the residuals in both X and Y. So instead of just Y, initially for OLS, this whole thing is a big 0. But now it has something, it's like something you can tweak, okay? I want to find some perturbations. Once I add perturbation to X, add perturbation to Y, now the two sets of X and Y can be perfectly related by this linear function, right? You think about all the wiggles. If I adjust them to both X and Y, once they line up on a line, then I have a perfect W to solve for. Now the goal is, so I can have many different kinds of, you can think when I have points, I can fit to any line. I can always add something to get each point to some line. But in the TLS, I'm trying to find the minimum perturbation that's required to make this happen, okay? So I'm not disturbing data too much. I'm modifying the data in order to fit a line. But I try to minimize the amount of change I add to the data in order to find the linear function. So here we have this f at the foot of this notation. That's called Frobenius norm. It sounds fancy, looks fancy, but it's just the Frobenius norm of a matrix. Is simply the element-wise squared. You square every element and add it up. Okay? It's just a very simple, straightforward extension to vector norm, L2 norm. Okay? There are many different matrix norms, but this is the most common one, Frobenius norm. So here, although we kind of ditched the map point of view, there's a nice kind of intuitive connection to probabilistic point of view. Here we are trying to, in MAP, we're trying to find the most likely value of Gaussian, okay, subject to the prior modification. But what is a Gaussian? Gaussian just this bump, right? If I want to find this, I want to find this peak. So in a way, I want to find minimize the distance to the mean, right? If I initially have my y, you know, when we do this, this becomes, you know, it's modified by something plus this. So this is the underlying model with some noise. So this just says, I want to minimize the distance from the mean, right? And the mean, in this case, noise is zero mean. So that's why I'm minimizing the Frobenius norm of this deviation, okay? So in a way, it sort of conforms to this, consistent with this probabilistic point of view. Why do I need to seek the minimum perturbation? It kind of resonates with the idea. If I change it little, very slight, as little as possible, yet I find a model, that means my distance to the true model is smallest. So come back to the TLS constraint equation. Y add some adjustment equals x add some adjustment times this linear combination coefficient. And it's very easy to turn into a matrix form, right? It's W multiplied by this, and Y, this term minus 1, since I move this to one side, okay? What does that mean, this equation? This, if this is a matrix, it's data matrix. This data matrix multiplied by this vector is 0. That means W minus 1 has to lie in the null space of this data matrix. Now, if this D is full rank, this will not be possible. Why is that? If D is full rank, what's in the null space? 0. And that cannot be, because here already you have a minus 1, right? W, no matter arbitrary W, it will not get you 0. So this cannot be, so in a way the intuition is this matrix cannot be full rank. If there's full rank, there's no solution. So, but here these are knobs, these are adjustments for us to choose. So the idea is that, you know, I want to choose EX and EY, add to it, so it becomes a, you know, not full rank. Okay? So we have this Eckert-Young low-rank approximation theorem. It states the following. Suppose I have an n by n matrix, and it's a rank. Of course, the rank is always then the minimum of these two dimensions. And we suppose it has this SVD decomposition, singular value decomposition. Then you pick a k less than or equal to R, the rank R. The AK takes this form. Essentially, is A itself is U S V transpose. S itself is S1, you know, SK plus 1, SR, and then 0 all the way, right? what this says is the best rank K approximation to A, if you just knock out every singular value on this diagonal beyond K. Okay? That's what it is. So this is what very intuitive. Right? If you want SK, Kth order, all the value, originally the A can be decomposed as is. There's no approximation. It's the full representation of A. But if I knock anything beyond a certain number out, in SVD the singular values are ranked from large to small, right? Anything that beyond K is knocked to 0, what's remaining is the best or rank K approximation. In what sense? In the Frobenius sense. If you calculate the distance between A and AK, and pick any other rank under K, matrix, this is always, the distance is always the smallest. It's the best approximation you can ever have. Okay? So let's understand this through, since we're only looking for this, y is just one dimension. Let's consider, for the time being, we assume xy is full rank, okay? And we want to, so what's the dimension of this matrix? X is n by d, y is n by 1. So this matrix n times d plus 1, yes? So I want to seek, if this is full rank, the rank is d plus 1. I want one less rank, so I want to seek k equals d, okay? Rank d approximation to this matrix. So we know that this is my matrix. I'm going to apply that theorem. This is my matrix A, okay? In the previous theorem, I'm going to apply this. This A, I'm going to do the SVD. So initially, the rank is d plus 1. So it's summing over from 1 all the way to d plus 1. Singular value, left eigenvector, right eigenvector, transpose. Now I have, when I add the perturbation, so the rank D approximation, I will have this, right? So I want to find this equation, right? So essentially I have this. So I'm gonna the solution is the rank D approximation to it. According to the theorem, I'm gonna knock out the last singular value. I'm gonna knock this out to 0, and so I get rid of the last summation. That's the best approximation I could have. And now if I compare these two, compare this equation 50 and 51, I would have the adjustment I need to make is the term that I get rid of, because this is essentially I equals 1 to D SI UI VI transpose plus the last term D plus 1 U D plus 1 V D plus 1 transpose. So the adjustment I have to make is this. I need to get rid of this one. Now, the null space of this, essentially null space of, the null space of this is the null space of this one. And I think what we want is x plus this, y plus this. Null space of this is null space of this. This is a mistake here. Okay? Because remember, the equation we want to solve is to find the null space of this one. Yes? W minus 1 lies in the null space of that. And that, we just substitute, plug that in. And what's the null space of this? it's essentially last vector, right? Because any of this, if you multiply d plus 1, the v, every column is orthogonal to each other. This is dot with the v, d plus 1 is always 0, right? So the null space of this must be spanned by the last singular vector. Okay? Basically, you have a bunch of v1 to vd, and the vd plus 1 is the null space of the previous d subspace. And then, since we are looking for this, this lies in null space of this one, and this is only one vector, we know that this has to be a linear, a scaled version of that. Now, again, this is only possible if the last element of this has to be non-zero. Okay? It requires that. So, let me see. I want to give the time to your questions, because now we have a new concept. Any questions up to this point? Then we can explain the negative regularization in next lecture. Any questions up to this point? What? Where's EX? EX is adjustment, we assume there's a noise in EX, EY. Yeah, okay. So this is take a different view. The X itself comes with noise, right? So I guess this is, this new concept takes some to sink in. So this is a generative model approach to look at the data generation. The data is, when you have measurements, there's noise in it. In the ordinary least square, I take a different approach. You know, the goal is still try to minimize the fitting error, but this linear approximation error point of view is the following. I'm going to seek adjustment made to data. In the OLS, I only allow the adjustment to be made to Y, no adjustment to X. Once I make these adjustments, I will find a perfectly fitted line. My best model is the one that makes the least adjustment, yet I obtain a line. It doesn't matter what that line is. I don't care about this. I only care about the best solution is the one that has a minimum adjustment, yet it falls into the family, the linear function family that I'm seeking. In the TLS, I allow myself the knobs adjustment I can make can be applied to both the X and Y. So you can think of, so I think maybe I can go ahead, look at this. In OLS, it's because I can only add adjustment to Y. The red points are my original data points. And I can come up with any line, but for this line is optimal in the sense that each Y, I only add this much, right? Each I adjust this much. If at this point I add something to it, if this point I minus some point to it. If I look at the size of this, in the Frobenius norm case, it's just a square error, right? Just a square version of this distance. This is smallest. If I take a different line, I can also fit a line like that, okay? If I do that, I will need to add adjustment. For this point, it will be this much. For this point, this much. You know, this I don't need to add much. This I have to add this much. This I have to add this much. Okay, so on and so forth. So my view have changed. It's like I have all these red points. I add these adjustment vector to it, so they all squashed to line up perfectly online. Okay? My best solution is the one that requires the least amount of such adjustments. So in a way, I have a lot of freedom because I'm fitting each point I have a y. This is n by 1 vector. But they have to be synchronized somehow so that everything leads to the same line. While for total least square regression, I allow to move the points in both x direction and y direction. I'm free to move. If I have something like this, I can move like that, you know. In the least square, it's always a vertical adjustment only because y is the one I'm allowed to move. X, consider no noise. You cannot do horizontal jogging, right? So the total least square, we will get to the mechanism. It's essentially is to the criterion, the intuition is that I'm seeking the adjustment thing is actually the orthogonal projection distance to any line. Okay, I want all these the orthogonal projection distances squared to be the minimum. Okay, so that's the intention. And in a way here you can already see, you know, if I want to fit a line, fit points with a TLS, I have no differentiation of x and y, right? I will not know. They're completely symmetrical. If it's a line, the only distinction is sometimes, you know, if it's a vertical or horizontal, you might have prediction error. But any slanted line, they're always one-to-one. So x and y has no distinction. But in the LS, you know, you're only seeking adjustment vertically. Vertical meaning I'm plotting this. This is my x, this is my y. That's why it's vertical. Okay? Any other questions? Yes?
This is back about kernels. When we talk about deriving the dual variation for ridge regression, does this relate to dual spaces like from linear algebra, or is it just dual in the sense of like, is it sex approach?
So the question is, we talk about, you know, probabilistic view to regression. We talk about the kernel view to regression, right? How we extend it in that direction. From the dual space, we get to the kernel view. Now we have this linear approximation view, low-rank linear approximation, regression, as seeking the low-rank approximation, right? So how are they related to each other? Is that a question?
I just meant more, you know, in the math that we did to derive the kernel, you know, this alternative formulation for ridge regression where we use the kernel trick, like what part of that do we use the concept of a dual space?
The fact that we derive the kernel relies on this you know, dual space derivation, right? Instead of seeking W in the primal space, we have to go express W as a linear combination of instances. That's coming from this, you know, null space component has to be 0. That's why I can express as such. If you think about least square solution, if it's underdetermined, I will have infinite amount of solutions, right? With ridge regression, that ambiguity is gone. But in the least square solution, you can have a solution in the range space. You can have any solution, you know, from the null space. The effect on prediction, the null space is non-existent. With the thing with the ridge regression is that, you know, it formalizes that we can always just, you know, focus on the range space solution. in the least square, I can only justify, the effective solution is the range space component. That's why. So if you look from the least square solution point of view, the primal representation allows you to figure out all these, null space variations. The dual solution has already got rid of it, so they are not equivalent representation, right? Dual space, sometimes the primal dual, something is made explicit, sometimes it's representing a subset of it. In the ridge regression though, because ridge regression solution is always unique and well-defined, they become one-on-one. With that view, I can represent the weights as well as the test evaluation results only based on inner products, and that's how the kernel comes into place. Today, we talk about low rank approximation. This is a completely different approach. In order to handle noise in X, all the previous things before today, we have not handled the noise in X. Okay? When there's noise in X, linear solution becomes, hard if not impossible. Okay? Okay, see you next week.